read the white paper of this presentation? One guy. You guys are kidding me? Okay, I spent so much time writing a proper white paper with all the details, how it works and stuff. So if you guys are serious about the security, you please download the white paper. I mean, the white paper is really cool. Let me show you the white paper. Okay, it looks badass academic with all references and stuff. Writing this takes ages. All right, so next time I don't come if you don't read the white paper. So the slides are on SlideShare. This is a presentation I actually gave a few times before. I gave it at the conference we do in France, which is called nullcon. I used to organize Akito with Philip, and like we sort of split up, and now we have like 2 good conferences. So they do Akito, and we do nullcon, which is focused only basically on reverse engineering and problem solving. The rationale behind it is that I think we've been doing, vulnerability assessment and stuff like that for way too long, and this fails at making a difference. Antivirus has been a failure over the past 20 years or so. I don't mean to be assaultive to anybody, right? But like, I think from a research perspective, we must focus on proving things, and if we want to have an impact in the industry, this is what is important. So in this respect, we have a conference which is focusing on this only. So the slides got a lot of attention. They've been downloading more than 80,000 times now. Usually when you do a good presentation at Black Hat, you get like 1,000 hits. So when you get like 80,000, it's like, okay, you put your finger on something important. Just a slide of introduction. So yeah, I'm French myself. Like we said, I have a pretty strong tie with India. I'm currently working in Sydney, but my company, we have a company in France and a branch in Australia. What we do essentially is working for the major companies in the world. Like, we don't do the top 500, we do the top 50. What we do for them is essentially due diligence. Like, instead of buying from data sheets, you wouldn't buy a car without test driving it, right? But what people do when they invest millions of dollars many times is like they buy from data sheets. Oh yeah, the vendor said it's cool, so it must be cool. And since, okay, this is reaching to an end, they essentially call me and they tell me like, okay, tell me what the vendor does not know about his own product. So we try to like do reverse engineering from a security standpoint, hopefully report a few vulnerabilities, and this is a good occasion to see how they behave. Like if they tell you, oh, we're not going to patch this, you say, okay, we're not buying your product. Or if they tell you, oh yeah, we need more money to patch it, that's cool, man, we're not buying your product. And essentially, this is actually making a change in the industry, little by little. So my English is terrible. I'm French. I live in Australia, so I have a terrible Aussie accent. If you guys don't understand what I'm saying, you please stop me and ask questions. All right, let's do it. So this is about hardware backdooring. Since I don't exactly like to feed script kiddies, I'm not making the malware itself available. That being said, you will soon understand that everything is actually built on top of open source, and this is one of the cool things about the backdoor itself. So if you're a researcher and you want to look at how it's built and would like to replicate or look for mitigations against this type of attacks, it should not be very hard for you to actually replicate the work I did. I'm telling everybody I spent a lot of time on this. It's a lie. I spent like 3 weekends. So the whole point of this proof of concept, why bother? The whole point is to prove that the Intel architecture is actually plagued by legacy and that it's, pardon my French, completely fucked. If you ask me, it's still the best platform we have. If you look at anything else like Power 7, Spark architecture, whatever, like those big irons, it's heap worse. So this is why I think it's interesting to have a deeper look at the architecture of Intel. The rationale behind it is that, okay, if you cannot trust your hardware, everything you're doing on top of it is nonsense, right? If the hardware itself, before being delivered to you, has been backdoored, any computation you're doing on it, it's nonsense. Okay, like I said during the introduction the other day, I like problems which cannot be fixed. And I think this is exactly what we should disclose at conferences, not to kill bugs, and to actually start a thought process or to fix stuff which is relevant to this industry. So in this case, you will see there is no solution to that. If you find one, like I'd be very happy to discuss this via email or whatever, or catch me up for Mommy, I quit smoking. Catch me up for a cigarette. Okay, another thing. So we're going to try to backdoor essentially the BIOS plus a few other things. I will show you. Some people told me, oh yeah, this has been done before. This is not cool, blah, blah, blah. We know it's possible. Right. What we know is possible is to target one BIOS. What we did here is target like 200 different motherboards. So that's 100 orders of magnitude better. By the way, I love the answer of Intel. I mean, when you go to Black Hat and stuff and your talk attracts a bit of attention, you got heaps of journalists asking you like, okay, we'd like to, to explain like what you've done and stuff like that. And they asked, I mean, Forbes magazine, for instance, interviewed me and asked Intel, what is your official stay on this? And the official answer from Intel was like, something like, yeah, we knew about it, blah, blah. It's not so cool. And 2 months later, Intel invited me to the internal security conference. So I think it's actually very relevant. So in terms of agenda, okay, I don't usually write backdoors. And if I write one, I want it to be super badass. I want it to be nation-state quality level, right? I want something, the ultimate backdoor. So we will see what are the specification of a state-level backdoor. I introduce you a bit of the Coreboot and the Intel architecture. Then we will see a bit of previous work, like the state of the art of rootkitting and ROM-kitting. Who's familiar with bootkitting, for instance? 1 person, 2, okay. So we'll spend a bit of time on this. Then I will introduce you the tool I wrote, which is called, interestingly, Rakshasa. So it's definitely, I mean, the tie to India is obvious, and it's an homage to India. I will show you how I designed the backdoor, and then we will talk a bit of supposedly mitigation that do not work, like full disk encryption and TPM. Any questions so far? Too easy? Let's do it. So I just did the introduction, blah, blah. Okay, a bit of FUD. So in case you've been hibernating over the past few years, what pretty much everybody, I mean, what the Americans are trying to lead you to believe is that China is the only evil on the internet and they're trying to take over the internet. It's less simple than that. From my understanding, it's like NSA has been doing that for a very, very long time. Right? China is trying to catch up, and there are a few countries who do what they can, like namely Russia, France, and India is not far behind. Anyway, so the Americans have a nice way to do it. They hire private companies to write documents for the governments, in this case the Senate, and this becomes the universal truth for everybody. So there was this report, which was identifying specifically the fact that, you know, when you buy a computer today, no matter what, it's built in China. If you buy routers and stuff like that, no matter what, it's built in China. And there is actually a risk of someone backdooring the supply chain itself. Like, even if, you know, the manufacturers are nice people, let's assume that, before your laptop is actually delivered to you, it goes into the hand of X people, and there is zero traceability. I mean, when you buy your new computer, like, okay, mine is a Lenovo, I have no idea who got this computer in their hands before, but implicitly you trust them. So yeah, in case you've never seen the internet recently, like let's say, I mean, who has read the Mendiant propaganda last week? It's like, it's all the Chinese blah, 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 okay? It's pretty alarming, the number of you know, FUD and stuff we get around China. I'm not saying that Chinese people are nice, right? I'm saying they're catching up. In France, it's even, I mean, one of the core problems is that everybody lost their capability to build their own infrastructure. So even in France, we used to have Alcatel, who was a big player, and then it got associated with Lucent, which is Bell Labs in the US, and we're not even building routers anymore. They're still built in China. So we discovered that, you know, it's a bit of a problem. I mean, the government realized that our core routers were all UI, and after or ZTE, and after the talk of FX at DEF CON, people were like, oh my God, maybe we should do something about it. In my opinion, like buying Alcatel is really cool because we get the backdoor of the NSA instead of the backdoor of the Chinese, but whatever. Okay, enough bullshit. Let's do a bit of technical stuff instead. I'm going to introduce you the problem. This is called the problem.
We can't hear you. Can you put the mic closer?
You guys can hear me? Is it better? Right. Oh, by the way, you didn't ask me why I'm wearing a suit, like yesterday and the day before. So the idea is that, you know, I think it's fairly easy and everybody can wear a tie, but not everybody can do reverse engineering. My father used to tell me two things when I was a kid. The first one is like, if you want to distinguish yourself, try to do it the positive way. So like instead of wearing shorts and stuff, wear a suit. The other one he used to tell me is, when you don't know, shut the fuck up. Sorry for my French. I tell that to my managers pretty often. Back to the problem. So this is the Intel architecture. So if we go to, from the bottom to the top, peripherals go faster and faster. Back in the days, you only had like keyboard, mouse, and floppy. This is connected to the Super I/O. Essentially, this is super slow. When you go to the north bridge, to the south bridge, you have like most peripherals you might be familiar with. Typically, your PCI devices, your Ethernet card, most peripherals really. And when you go to the, closer to the CPU, so to the north bridge layer, you have much faster peripherals, like your video, and typically PCI Express, like, you know, if you have like gigabit Ethernet, for instance, is going to be much faster, so it's going to be connected to the north bridge. Nowadays, they are like crosses, like they sort of fusion the north bridge with the CPU for performance reason. So why is this super bad and fucked? There are two reasons. You might have noticed TPM over there, which is fairly low in the food chain, where it's supposed to be like the security device. Who knows what's a TPM chip? Yep, what is it? Yeah, but what does it do?
It has a hardware key, the hardware itself, which can never change.
So essentially, it's a cryptographic coprocessor. All you said is true. It can hold, I mean, it does hold RSA cryptographic key, well, that you can use for RSA signing at least. Do you guys know where the TPM core root of trust is assembled? This came up on Twitter last week. It comes from China, baby. The core root of trust is Chinese. The other problem is that at every layer, one component can control the other components. So like your CD-ROM drive, which would be typically on the south bridge, can control your network card, which is completely counterintuitive, and it's, I mean, from a security standpoint, it's definitely not what you want. But this is legacy from the 80s, right? This design has not changed since the first IBM computer, which was designed around like, 1980. Sounds good, eh? Okay, just a bit of what has been done before in this field, so you can have an idea of why this might be innovative. So the first viruses, you'd like that. The first one was apparently made in Pakistan. It was called Brain. I mean, the first viruses were cool because they were super low level. People were doing like master boot record. and like they wanted early execution. I mean, back in the MS-DOS days anyway, we had like, it was single process, right? The operating system did not support proper multitasking. We had to cheat with like stain memory and stay resident routines, which was actually like super bad. Who has done assembly back in the MS-DOS days? One person. Okay, you might understand the talk. So for a while after in the late 90s and early 2000, so people started to connect to the internet, and from a malware perspective, there was a huge drop in quality. People started to spread like VBS script and stuff like that, which was very high level, but completely uninteresting from a system programming point of view. And back in 2007, people started to look back at EFI, which was before UEFI. It was the first standard, which is now deprecated. But anyway, so that guy from NGS managed to actually bootkit UEFI. I will explain you later what is a bootkit. Then in 2009, we got the guys from security. This work is amazing. There's a paper in Frac magazine also, and a presentation at Consequest. They basically took a BIOS, they patched it, they identified the routine for checksumming the integrity of the BIOS. They introduced their own routines, and they compensated the checksums. This is doing it the hard way. This is what I don't want to do, because there are so many platforms. I don't want to have to do that per platform. But this is pioneering work. In 2009, Peter Kleichner from Austria wrote a cool tool, which is called the Stone Bootkit, which is capable of bootkitting not only Windows, but also TrueCrypt. So it showed that essentially, we don't really care if the full disk is encrypted. In 2010, the Kumar and Kumar brother, who are from Hindustan, wrote vBootkit, which was the first bootkit for Windows 7. Piotr Bania, who's a complete alien, he lives in Poland. He actually helped me with this talk, with the bootkitting part. I will show you, but let's give him credit. He wrote the first bootkit to bootkit any Windows 32-bit or 64-bit. And currently, his bootkit also supports Windows 8 if you're not using UEFI. So my prediction is that one of the big topics for Black Hat this year is going to be bootkitting UEFI. Actually, it's going to be a big topic for NoSuchCon, if you come to my conference. And I can tell you already, we destroyed TPM. But you have to come to the conference to see that. And in 2012, Snare, who's a good friend from Australia, he's really cool, wrote a bootkit for UEFI, but for Mac only. All right, let's talk about Rakshasa. So if I make a backdoor, I want it to be persistent. Not only persistent across reboot, I want it to be persistent forever. Even if you change parts of the operating system, or like you remove the hard drive, you put another one, I still want you to be infected. If you remove some peripherals, like you remove your network card, you put another one, I still want you to be infected. I want that kind of persistent. I want it stealth, so I want zero code on the hard drive, period. So like attack surface for an antivirus, I mean, if you're from the perspective of a malware writer, antivirus is the attacker, right? And I want him to have zero attack surface. If possible, I'd like it to be portable, so operating system independent, whether you're using like Linux, any version of Windows, BSD, I want you to be on forever. Of course, I want remote access over the wire. I want, if possible, to push remote updates. Okay, if you do a backdoor which has to be state quality, there are essentially two clauses you have to respect. The first one is called plausible deniability. It's saying, oh, and every attack done by a government respects that. It's saying, no, it was not an attack, it was a mistake. And it has to lose plausible. That's actually very important, because if you discovered, you can still claim like, nah, this is a conspiracy theory. You guys are hallucinating, right? And the other one is called non-attribution. It's the fact of saying, nah, it wasn't me, it was China. So if possible, I'd like my backdoor to actually cross network perimeters. So like, you know, if you to attack either a government agency or a large company, it's fairly reasonable to assume they do have firewalls with authentication, they do have network segregation. It's not always true, but like, let's assume the worst case scenario. So yeah, firewalls, authentication proxies, it goes without saying, I don't want the thing to be detected by antiviruses, but okay, that's not really the hot bit. I want it to bypass like IDS, IPS, all those things. And I'd like some degree of redundancy in case something goes wrong. Looks like something reasonable for the perfect backdoor? Would you like to add something? All right, so let's try to do that. So this is a typical corporate network. You have the end user who's, I mean, the quality of, I mean, they perceive the quality of their computer by the color of it, usually. Before reaching the internet, you have a big fat firewall with authentication proxy, which means, and it does proper, let's assume it does proper DNS segregation and stuff like that, so you cannot cheat and do TCP over DNS, for instance. The only way to exit to the internet is actually first to authenticate to the proxy, period. And in the middle, you can have some toys like IDS, IPS, deep packet inspection, all those stuff that do not really work. That looks like a typical network proxy. I mean, a network of a large company? Okay, so what is supposed to happen is the end user is going to authenticate via Active Directory or whatever protocol to the authentication proxy, and then only they have access to the cloud. So the first thing we can do, if we're attacking end users, is something like this. We sit in the parking slot with the Wi-Fi, and we get the BIOS to, I mean, if the BIOS has its own Wi-Fi stack, so it's not asking permission to like, you know, Windows or whatever, if the BIOS has its own network stack, we can just have the user to connect to the Wi-Fi of the attacker. It doesn't have to be every day or whatever, right? It's like at boot time, once in a while, if I own you that way, it's good enough. So if you do that, you essentially own, I mean, you bypass the design of modern corporations. So what to do all that stuff? I mean, it looks fairly complicated, right? If you have to write your own BIOS, it's going to take you a few decades, probably. I mean, the amount of reverse engineering using GTAG debugging and stuff like that is just insane. Most people do not publish data sheets. So what I use is actually open source components. And we will see that this has nice side effects from an antivirus perspective. So the main software is called Coreboot. The rationale behind it is that a few years ago, I was talking at CCC, and I met the guys from Coreboot. So the idea of those guys, they're fanatics. What they said is like, okay, we want an open source laptop, but not just the operating system. We want every firmware to be open source. So I said, okay, let's write an open source BIOS. It used to be called Linux BIOS, and now it's called Coreboot. And it's still a project which is very much alive. And those guys are crazy. Like, they actually take BIOSes, which are proprietary, and they reverse it using GTAG, and they make an alternative, an equivalent open source software. It's a lot of work. So they did most of the work for me, really. Coreboot is really the back end of the BIOS, which is responsible for the BIOS post. It means that it's responsible, it's the first, I mean, you guys know our computer boots. So it first starts in legacy 16-bit real mode for compatibility reason. And the first thing the CPU does is transfer the control to the BIOS. So from a malware perspective, if you're the BIOS, you execute before anything else, right? So Coreboot is responsible only for this, the BIOS post, like discovering what are your peripherals, discovering your RAM, your hard drive, and stuff like that. Then CBIOS is the front end of the BIOS. It's a thing which is, if you know system programming a bit before UEFI, all we've been using is an interrupt vector table in the first page of RAM, right? So CBIOS is responsible for setting this interrupt vector table and actually mapping every entry in the interrupt vector table to some routines who actually talk to the hardware. This is as low level as it gets in terms of system programming. I was asking about MS-DOS because back in the days we didn't have segregation, and you could, from MS-DOS, program the hardware directly, like call interruption, interruption 10 or interruption 16 to talk directly to the BIOS, interruption 13 to talk directly to the hard drive. And I mean, nowadays, once you have a proper kernel which has booted to a protected mode, to have multitasking and stuff, you don't have access to that layer anymore. You have to go through the kernel. I'm also using iPXE, which is an extension of PXE. Who knows what's PXE? Wow. Okay, so PXE is a network protocol to do remote booting. It's for diskless stations. Essentially, the idea behind it is like, okay, I have a computer without a hard drive. It boots from the network. So it works that way. You acquire an IP from the network of a DHCP, and the DHCP server also tells you where to get an image of your hard drive, of the system. And then everything happens in memory. So like, you download over TFTP the image of a hard drive, and you boot that stuff from RAM. It was designed by IBM and Intel like a few years ago. iPXE is much better. It can use like, it's an extension of that. You don't have to use TFTP. You can use FTP, but you can use also, it has the stacks built in for, so FTP, HTTP, HTTPS, and all of this can be fit into an expansion ROM, which you can flash on a network card. So if I take your network card, I flash it with iPXE, all those stacks are going to be built in. And I'm using a bunch of payloads, namely mostly Coreboot. And the cool stuff is that we're going to support 230 motherboards without writing them. Like, I'm not writing the PCI expansion ROM or the BIOS. This is the list of supported motherboards by Coreboot. So imagine the job done by the guys of core security. It's one line. You understand why it's slightly better? Any questions so far? Okay, it's going to become clearer and easier. So what we're going to do is, okay, Coreboot is very modular. The idea is that inside your BIOS ROM, you have actually plenty of space. And you can put other PCI expansion ROMs to control PCI devices, like either your CD-ROM card, your network card, or whatever PCI related software, straight into the BIOS. So what I'm going to do is take the iPXE thing and put it inside the BIOS and flash your BIOS with my malware. For redundancy, we can flash not only the BIOS, the main BIOS, but any other PCI firmware we want. Typically your network card, it's a good target. But I could flash also with the same firmware your CD-ROM, because the CD-ROM is at the same layer on the soft bridge, and it can control your network card. And this gives me a bit of redundancy. So since I'm evil, I'm not going to put anything malicious on the hardware, so that if you send it for forensic analysis, there is nothing on it. Everything which is malicious, the bootkit, I will explain you in an instant what a bootkit is, it's fetched over the network every time. So it works in a CNC model thing, right? I can have my botnet at BIOS layer. And if I'm not happy or I think that you guys discovered my attack, I just shut down the CNC, you don't get the hostile code at all. And okay, if you boot over Wi-Fi or WiMAX, because iPXE has a Wi-Fi and a WiMAX stack, which we can put directly into your BIOS. I mean, this is sick. It's your BIOS speaks Wi-Fi, your BIOS is going to speak WiMAX, and your BIOS is going to speak all the upper layer protocols up to SSL. Okay? So I can do HTTPS from the BIOS. Yeah, that's sexy, baby. And we'll see that this gives you the opportunity even to reflash the BIOS remotely or the network card remotely if you want. So we work that way. We have Coreboot, which is the backend of the BIOS. On top of it, we have CBIOS, which initializes the interrupt vector table. And on top of it, we have a bunch of PCI firmwares. Typically, the main driver is going to be iPXE to have all those network stacks. So this is not malicious, right? It's legitimate software, and people use it not only for backdooring. So from an antivirus perspective, you cannot tell me that you're going to blacklist this. There is nothing to find. And it's the only stuff I'm putting on your box. And whenever you boot, I'm going to fetch the bootkit over HTTPS. Possibly, iPXE supports client-side certificates, which means what? If you have an IPS, you're not seeing anything. Even if you MITMing SSL, worst case scenario is going to fail, but you won't get my magic bootkit. Any questions so far? Okay, I must explain you what a bootkit is, because maybe it's not too clear to everybody. So the idea of a bootkit, it was initially a piece of software you would boot on. Instead of booting from the first hard drive, you would boot from an alternate media, either a CD-ROM, a floppy, or a USB pen drive. This stuff would initialize some memory, I'm going to explain better, and then transfer execution to the hard drive, the main hard drive. And when your operating system is unpacked in memory, right, the bootkit is going to actually patch the kernel in memory. Okay, that was the version for kiddies. Now let's go for the real version. Okay, a bootkit is this. It's a piece of software which hijacks interruption 13 in the interrupt vector table. Interruption 13 is the only way to interact with hard drives at all. After BIOS post in the BIOS, what happened is that, so during BIOS post, the BIOS finds your RAM, finds your first hard drive, the first bootable hard drive. The first sector, which is 512 bytes of the first hard drive, is called the master boot record. When it has done all of this, the BIOS is supposed to give execution to the master boot record. To do that, it executes interruption 19. What interruption 19 does is load the master boot record from the first disk to a given page in memory, which is standard. It's 0. I mean, segment register is going to be 0. And the offset is 7C00. Okay? So it takes this, it takes the master boot record in memory, it puts it in RAM, and it jumps to the entry point of the master boot record. The only role of the master boot record is to make sure that we can take the kernel from memory, unpack it live in memory, and jump to the entry point of the kernel. And then the first thing the kernel does is switching to protected mode. Okay? That was too easy? Okay, so the bootkit hijacks interruption 13. By doing so, every time the master boot record is going to try to access the disk to unpack the kernel, we can say, okay, you're trying to read this page or that page, and I don't have to give you the exact same page. I can proxy it and I can patch the unpacking thing in memory. The idea being, so there are two kinds of bootkits. The simpler kind of bootkit, which I've been using here, has no payload. What it does is it patches the authentication routine of Windows in kernel land so that you can authenticate using any user and using any password. Okay? It just patches the authentication routine. More evil bootkits like Stone, they do something much better, or TDSS, if you've seen that thing, which infected shitload of company last year. What they do is load a signed kernel module in memory, sorry, an unsigned kernel module in memory. You must know that starting with Windows 7, 64-bit, every kernel driver is supposed to be signed. So if I can, before anything, load an unsigned kernel module in memory, I win. I can execute in userland whatever I want as system. I can kill any process I want. I don't have to let the antivirus start. It's game over. Okay? So that's what a bootkit does. Features. Woohoo! Let's go for the hard bit. That was the easy part so far. We're going to try to remove the NX bit. Who knows what the NX bit? Are you guys kidding me? You're not writing exploits? I mean, back in the days, Intel CPU were as shitty as IBM CPUs, which means everything which was mapped in memory was read, write, execute. It's actually not true. It was either read, execute, or write, execute. But it means that everything which was in memory was executable. This is terrible from an exploitation perspective. It means, for instance, your stack was executable, or your heap was executable, which is completely pointless. So we're going to remove this bit. So everything is going to be executable again, meaning that next time that web devel reports a bug which is supposed to be non-exploitable, well, in your scenario, it's actually going to be exploitable, baby. We're going to flip one bit in ring 0 so that every page in ring 0 becomes writable again. We can remove CPU. OK, you guys know how Intel is patching CPUs when they have bugs? They're not asking all the CPUs back. They push microcodes on it. And this is done typically at BIOS level. Since I'm the BIOS, I don't have to push any microcode. So we're going to remove that. If you're familiar with SMM, am I running late? OK, I'm going to take a bit of. Is there a talk right now? Maybe? OK, so I'm going to speed up. We're going to remove any SMM-related protection, which means we're going to know at least one way to elevate privileges locally in a deterministic way, and you cannot do anything about it. It's by switching the CPU mode to system management mode, which gives you a way to execute stuff in ring -1. We're going to disable ASLR, possibly for any operating system. We're going to remotely boot a bootkit. And if you have all of this, your security is back in the 80s or something like this. 5 minutes? Right. I'm going to be a bit late. So how do you remove NX? NX is a model-specific register. If you look at the AMD manual, it's actually bit 11 in a given register. So the idea is like we just need to flip it. Long story short, we use the CPU ID assembly instruction to verify if NX is actually supported. If it's supported, we actually read the model-specific register, flip 1 byte, write the model-specific register back. NX is gone, period. So control register 0 as a given bit, which controls write protection in ring 0. It means for the kernel. So same thing, you flip 1 bit. You don't even need like model-specific registers or whatever. You just read CR0 into EAX, saying you're in 32-bit. You mask it, you write it back, period. You can write to any page in the kernel. For microcodes, it's fairly easy. There is a directory in Coreboot which contains all the microcode. We just remove it. SMM, OK, that's a whole story by itself. Look at the work from Loïc Duflo at Consequest. Actually, Coreboot does not support SMM protections, so I had nothing to do. Disable ASLR, this is tough. Essentially, if you have full ASLR, it has to be done in kernel land. I'm not entering into the details, but like if you identify where the seed for randomization is in kernel land, and the Kumar and Kumar guys who are Indian found it for Windows 7, you just patch that with 41, 41, 41, 41, and every mapping is going to be repeatable forever. So if you do all of that, your overall security goes back to about the layer of 1997. And you cannot know anything about it, and you don't even see any artifact of it. And even if you switch, like you remove the operating system and you put Windows 8 or whatever, like it's pointless. It has been done before. OK, so in terms of stealthiness, I think it's pretty obvious that, OK, we're using legitimate code. So from an attack perspective, as an antivirus, there's 0 attack surface, because there's no style code, unless you start flagging Coreboot or iPXE, which are legitimate software, as evil. There is nothing on the hard drive anyway. So like, I mean, most people, I do a bit of forensic analysis with my company. Usually what people do is send us a hard drive. There's nothing on the hard drive in this case. And even from a network perspective, if you do it over Wi-Fi or WiMAX, Like, okay, I don't know any IPS, which is capable, if I am the base station, to actually man in the middle of the traffic or anything. And cool stuff, we can use, if we want, the CMOS, because Coreboot has its own CMOS emulation, which is, CMOS is an NVRAM. Normally it's used for configuration of your BIOS. Since Coreboot has its own emulation, we can use the real CMOS chip to store, for instance, cryptographic key. Portability, I didn't have to do anything. Like I explained to you, 230 motherboards are supported by Coreboot, so we can actually flash Rakshasa on 230 different motherboards. You need to rebuild it for every target, though. You cannot have one build which is going to work for every computer. In terms of modularity, you can put all those bits, like the PCI expansion ROM, the bootkit if you want, and any other software straight into the BIOS, because Coreboot allows that. But I think it's better to fetch it over the network for updates and modularity. Demo, evil kernel, evil remote kernel on edge of death. So thank you for staying until now. I know it was a bit technical, and can you guys read that? I'm using KVM. I'm booting a different BIOS from the original one, which is called Rakshasa. I'm setting a Wireshark just to sniff the HTTP traffic. I'm doing this into an emulator, because if I do that on a read box, you won't see anything. So we're going to do this via KVM. Okay, so KVM is booting Windows, as expected. And like I told you, for bootkitting, you don't have to know the password. At this time, you can type any password you want. I just typed enter. Let's see what happened at network layer. So there were actually two HTTP connections to the CNC. The first one, okay, it's sending a bunch of parameters back to the CNC, like your IP address, your net mask, what is first DNS given by DHCP. Then the first file downloaded is actually another IPXE configuration. You could download the bootkit straight away, but it's better to do pivoting like that, because I can change this file. And this file tells the BIOS where to find a kernel image and a disk-based image, okay? Which is in this case, the init.erd is really my bootkit. So you can see here that it was memdisk, which was the kernel downloaded. And what I use as init.erd is actually my modified version of Coreboot, which is just modified thanks to Piotr Bania to be entirely silent. Normally you have like fancy designs and stuff, but for malware I don't really want that. Okay, so as you saw, like it booted in 1 second. There's no noticeable delay or whatever, but it actually booted over the internet a kernel, a bootkit, patched the kernel in memory, and allowed me to authenticate without using a password. Yeah, right, I cannot afford a Windows license. If we look at the version of Windows, this is actually a Windows 7 64-bit. And the latest version of Coreboot even supports Windows 8 if you don't have UEFI. And if you have UEFI, come to NoSuchCon, we explain you how to destroy TPM. This is cooler than XSS or what? Okay, Windows 7 Ultimate, Service Pack 1, 64-bit. Internet amaraye. Okay, let's look at what happened on the server side. If I looked at the server logs, so obviously I have all the information which was sent, like IP address, domain name and stuff like that, which allows me to specifically know who I'm targeting. You can even add like a different ID for every victim if you want. Now, nice feature. Okay, you did not see that because it was too fast, but the IPXE configuration actually told them to exploit a web service on the way. Yeah, I know how to do web service exploitation too. In this case, so it's this IP address, don't look at it. And it allowed me to send an email from the BIOS to the owner of the BIOS botnet. It's sending me information just like netmask, gateway, and DNS. I'll just be 2 more minutes. That was cool or what? Thank you. So in terms of modularity of iPXE, you can put the iPXE configuration file on the BIOS, but it's better to fetch it over time from HTTPS because you can change the parameters. You can tell the BIOS, okay, you try to acquire an IP address over DHCP. If it fails, I'm going to give you this network parameter. So try to assume that 1.9.168.0.1, for instance, is a gateway, and take IP address, blah, 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 all 3. We can send back information to the CNC. We can even authenticate using admin credentials over HTTP auth. It supports basic auth. So like if you're a home user, I can try to reconfigure your own router from the BIOS. This is all to send back an email to the owner of the botnet. We can do router farming, like change the password on your DSL router if you have one. And change bootloader. This is the stuff I explained, like, yeah, we're going to fetch another configuration file instead of hard coding it. More demos. Okay, so people told me there's a big problem with your stuff. Like the graphics don't look like a legitimate BIOS. So let me show you what other people did in terms of designing something. This is booted straight from the BIOS. Oh, you're not seeing anything. Okay. Can you see this? I'm playing Invaders. Okay, it doesn't see. Okay, long story short, you can do any design you want. It's just because I'm lazy and I don't want to spend time on this. So Apache log, we get mails back from the BIOS. You can do same thing, SMS back from the BIOS if you want. Let me show you quickly how to create a botnet nobody can shut down. So it's fairly common to have like rotative IP addresses. I know, man. To have an algorithm to pick up where the CNC is and have several CNCs. What I suggest to do, if you just want to be the command and control once in a while, you take all the IPs of the internet and you rotate, you try to boot out of that. The risk is that obviously agencies could hijack your botnet easily, right? Because like if they own your CNC, they can shut it down. So to avoid that, you just use asymmetric cryptography with client-side certificates, and they cannot even perform the initial SSL connection, and they cannot take your botnet down. Okay, why crypto won't save you? Okay, so the idea is that even if you're using TPM and stuff, when you buy your computer, the disk is not encrypted. If the disk is encrypted, you have another problem because it's encrypted with a password you don't know, right? So even if you're using like TPM and Windows 7 or Windows 8 and full disk encryption, not to mention that full disk encryption has been bootkitted already, when people give you your laptop, nothing is encrypted and the TPM is not sealed. If you want to see, yeah, there again, I don't want to spoil it, but like if you want to see how to actually destroy TPM, come to AutoCAD, no such con. Antivirus. So the only bit, to me, using an antivirus on a server is like putting lipstick on your server. So the only bit which was actually malicious was the bootkit. I used a 3-year-old bootkit, slightly recrafted to remove the designs. Okay, you take a 3-year-old bootkit, you upload it to VirusTotal, we get a detection ratio of 2/33. you use a simple packer which is called LZMA. It's the most standard you can have. It's used by default by the Linux kernel nowadays and every PCI expansion ROM. And the ratio drops to 0. Antivirus for the win. Okay, we don't have time for that. You'll read the slides. When you buy a network card from eBay, the firmware could be infected with Rakshasa, so don't do that. Backdooring the data center. You can actually, in VMware, you can specify which BIOS you want to boot from. So if your servers are virtualized, you have actually no way, as a guest, to know which BIOS is actually booted. And it's actually entirely possible for the person in the data center to specify in the configuration file Rakshasa as the default BIOS, which means every guest is going to boot Rakshasa silently. Remediation. Okay, if you get an intrusion, you have no way to know that people did not push that into your servers. So you take your server and you dump it. You'd never use a compromised server again. If you really want to do it, okay, the right way to do it is before you install anything on your computer, your laptop or your servers, you take an image of every firmware, you measure it using you know, MD5, SHA-1, whatever. And you cannot do that while the computer is booted, because if you do that, you implicitly trust your hardware already. So you have to do it using FPGA and actually extract the firmware from every peripheral. And once you got an intrusion or when you want to verify integrity, you do the same thing again and verify the checksums. Who does that? Nobody. It's too costly. So I really reckon, like, if you get an intrusion, like, you cannot trust your hardware again. Too easy, too easy. We can boot from a SAN. All right, you check the slides. It doesn't matter. Any questions? If you don't ask questions, I'm not coming back next year. Okay, thank you for your time.